and answer the following questions. Okay, where are fuel injector nozzles installed on an engine? In the cylinder heads near the intake boards. That is correct. What is a metering orifice? Well, particularly in this application, that's a perfect answer. An opening inside the fuel nozzle that provides a specific flow rate, plus or minus a couple percent. Yeah. What is an emulsion? A mixing of two substances, especially, oops, why won't this type? Enable editing. There we go, get rid of that. Mixing those two substances, especially substances that don't like to mix. In this case, air and fuel, right? Yeah, does that make sense, Vincent? Oil and water would be another example. All right. Okay, how is upper deck air supplied to the fuel nozzles? Upper deck air feeds through the air bleed. So upper deck air, there's going to be a series of hoses on the engine. Fairly small diameter, maybe 3/8 of an inch, is going to feed air to the outside of the nozzles. All right, what features of the fuel injection nozzle break up the surface tension of the fuel? There's two. Yeah, the little extension is on the fuel nozzles themselves. Let's see if I can pull this up. This little extension right there, that what you're talking about, Interveer? Yeah, and then this will be plumbed through some hoses to the turbocharger. Okay, so what features of the fuel injection nozzle break up the surface tension of the fuel? So it's the discharge port. I don't. Well, the discharge port, where is the discharge port threaded into? Raiden? Into the cylinder head, right. But that's not where my high pressure air comes from. My high pressure air, there's the discharge port on this one. My high pressure air is going to go there. Does that make sense? I can pull this into a slide. Are you seeing what I'm pointing at? Let me put this into the actual slideshow so I can get a pointer. This is the discharge port. That's going to have low pressure fuel air emulsion leaving the nozzle. I'm going to have fuel going in right here, and this is for a turbocharged, so we're going to add air right there. In this nozzle, a simpler nozzle, or this nozzle here, B is the same as A. A is just a cutaway version of B, a cutaway drawing of B. The fuel goes in the top. Air is going to come past this shroud through the air bleed holes, and then fuel and air emulsion will come out the bottom. Does that make sense, Braden? All right, back to the... Okay, so what features in this fuel injection nozzle break up the surface tension of the fuel? Well, that would be the air bleed and then the emulsion chamber. This one doesn't show the emulsion chamber the same way. Oops. There's another drawing I thought that actually had a little, oh, there we go. This one here labels the emulsion chamber. So the emulsion chamber and the air bleed hole work together to make our fuel break up into little droplets. Okay. Back here. How do we determine the size? Okay, so that's how you would decide on what size. How you can determine the size is by reading the little letter on the side, A, B, or C. Who you got? Yeah, you got that perfect there. I think you're answering the question. So the answer to this question here, how do we determine the orifice size? It's kind of somebody else's job to tell us what to put in, but the jet size is determined by the letter code A, B, or C. So we're going to go with and standard fuel injectors. That's wrong. They can so. Why not? Where's my strike through? Yes. Oops. Yes. Yes, they can. Get rid of that. Nozzles of same type are interchangeable between engines and cylinders. Exactly. Exactly. If I got an A on one engine, I can just go and toss it onto another engine. What type of nozzles are not interchangeable? Gammy, thank you. All right. Why do we install the air blade upwards? So that fuel doesn't leak out. Very good. What is the nozzle flow comparison check for it? Equal fuel flow levels between nozzles. Yeah, if I get a bunch of C nozzles, they should all flow exactly the same. If you had Gammy nozzles, you should see it run in sets. The back two cylinders, the middle two cylinders, and the front two cylinders should all have the same kind of fuel flow. All right, if a set of B nozzles was replaced with C, the fuel flow would increase. Pressure would probably decrease a little bit, but the indication would be all messed up. It would be indicating lower than what we got. So that's a good answer there. Because in a naturally aspirated engine, ambient pressure is higher than manifold pressure. Exactly. So our air bleed works properly. And turbocharged needs it because it's lower and we blow our air backwards. Upper deck pressure. This question here, you missed that one. That's the pressure coming straight off the turbo. Oh, there we go. Perfect, you did answer. Just kind of went over a line. How is the fuel air mixture adjusted in flight? Using the mixture control, forward for more fuel, retarded for less, and it is tweaked with your eye focused on which gauge. What gauge is the pilot going to watch when they're adjusting the fuel air mixture in flight? No. You're going to watch the exhaust gas temperature. And they're going to pull that lever back, and the exhaust gases will get hotter and hotter and hotter, and then they'll start to get cooler and cooler and cooler. And you'll either run on the lean side of that peak or on the rich side of the peak. Rich side is generally considered safer. The lean side is considered, it's cheaper and more fuel efficient if you can do it safely. Does that make sense? Retarded for less, forward for more. You watch the exhaust gas temperature. Yeah, and you can it's mostly the improved gas mileage. The cylinder head temperature we're going to control other ways. That's getting into a subtlety that's hard to I would consider just look at your improved gas mileage. Managing run of Richard peak, more power, generally considered safer as well. Let's just take that one off. It can, well, I won't take it off. It's not untrue, but I don't want you to get too confused because running lean can often give you a high cylinder head temperature as well. Out of GAMI? Yeah, exactly. Making the range of EGTs between the cylinders smaller, and that allows us to run on that lean of peak. Okay. Perfect answer there. Perfect answer there. How do fuel injection systems? Yeah, near the cylinder. Cylinders are really hot. You don't end up with ice if you do it there. Whereas at your carburetor, or if you're injected into the venturi throat, that's farther away from the engine, and it's a naturally cold place on the engine. And if you put something to evaporate and cool in a cold section, it gets really cold. Travis, what's your question? See, my attitude a little bit here is you haven't sent me in anything to review, so I would prefer I kind of moving along at a little bit of a which one are you looking at here? Which is your question and what is your answer? Ah, this one here. So that gets back to, let's go. Draw here. We've got cylinder number, oops, I need a pen, not a pointer. Got a pen. I got cylinder number 1. I got cylinder number 3. And I got cylinder number 5. So we're looking at one side of the engine here. And we're going to have the propeller is going to be right here. And I'm going to have this runner updraft. And I'm going to go ahead and have all of my fuel and air is going to be coming in here. If I put in fuel, let's make our fuel orange. If I put my fuel in right there, there's going to be a period of time where some of this fuel dribbles down there. Some of this fuel dribbles down there, and some of this fuel dribbles down there. The fuel that dribbles down here will get pushed along, and here will get pushed along. So this one's going to run lean, and this one's going to run rich. This one's going to run middle, right? So to compensate for that with GAMI, we put in less here, and we put in more here. That explain, Travis? All right. Back to all right, so how does the fuel injection system reduce individual system cylinder overheating? It improves fuel distribution. Perfect. I like that answer. Now, what happens when the fuel pressure falls too low? The fuel will shut off, right? Fuel flow stops. Stops. Engine quits. Perfect, right? Okay, pounds per air hour. Okay, so how is the fuel flow measured? Pounds per hour or gallons per hour. per hour. Change over this to red. It is actually pressure reading. Does that make sense? Actually a pressure reading gauge, but we deliver the information to the pilot in pounds per hour or gallons per hour. Right. So if we took out B nozzles and put in C nozzles, we would increase the fuel flow, but not the indication. Ooh, okay. So this one here, I think we've got a little bit of a misunderstanding. If you had a clogged fuel nozzle, you're not going to see much in the cockpit because one nozzle being clogged a little bit, because if it's clogged completely, that cylinder is going to die, but that's not what tends to happen. What tends to happen is you get a little bit of a piece of hair or flake of rust or something in there, and instead of delivering 9 gallons per hour, it delivers 8.7, and that cylinder runs lean, and the indication you would probably get in the cockpit is that cylinder running hot, and that'll be the same symptoms, indications that you'll get with a kink or partial crush in a fuel injector line. It'll run hot, you might get backfiring, you might get detonation in that one cylinder. And if you get clogging in there, you would get less fuel through the clogged nozzle. And the fuel flow reading will not be much change. This is going to actually be pretty darn close. I'm going to disagree. You might end up with a fuel flow reading that is higher than what you're actually delivering. You might think you're delivering 10 and you're only delivering 9.8. But so some misunderstanding there. Clogged fuel nozzle is going to decrease the fuel flow, but not the reading. It's going to decrease the fuel flow to one cylinder in particular, which might make it run lean. Well, will make it run lean. It may run hot, it may backfire, and it may detonate. Okay. Any questions on that? Or did my explanation help? Okay. All right, is fuel delivery time to the engine rotation? No. Correct. Air metering force. Impact and Venturi? Yes, exactly. We just talked about that. This becomes a usable force? Exactly. Well understood. How would it change in airflow? Shifts the air metering force. So an increase in airflow means an increase in air metering force. That's pretty simple. What is the Venturi? Creates a pressure. It basically, in my terminology, measures the airflow. Exactly. Fuel metering force, inlet pressure and metered fuel pressure. And we get that metered fuel pressure with two valves. The mixture control valve, controlled by the red handle in the cockpit, and that second valve that is linked to the throttle plate position. What does this force do? It affects that ball valve. I think you kind of got that. What determines the fuel metering force? Beats me. I think this is understood now because I talked about it. Inlet pressure gets reduced when it has to go through two valves. They oppose each other. The air metering force acts to increase fuel flow, and the fuel metering force acts to decrease fuel flow. Which control is used to shut off the fuel when the engine pushes it? No. When you pull the throttle back to 0, the engine had better not die. It had better settle in at a nice 650 RPM idle speed. Which control, please, is used to shut off fuel to the engine? There is no idle cutoff control. There is no control that is called the idle cutoff control. The main mixture hold back to ICO. Okay. And the idle valve is never closed. This valve never gets closed. We just open more valves or bigger. So let's look back at, we need to look in here to understand what's going on here. We have got two valves. This one here, let's erase all this, is linked to the red handle. When we want to go to idle cutoff position, we close this completely. And now no fuel can go through and get to the orange. And if you remember, the orange in this case is blue, just to confuse you. The orange is this line here. And so none of it can get to the engine. The idle valve is built onto this side. And if you can see here, this is the mixer control valve. Here's our main metering jet. And if you can see, the idle jet is just this little section in the main metering jet. And it goes open and then way more open. So does that make sense? Two valves, one controlled by a dedicated control in the cockpit, our main mixture control. Okay, I'm going to make a special name for this. Constant head idle spring. Okay, so I'm not surprised this one was a little tougher because the student who did this did it before we taught the Bendix. So that's okay. There's going to be a little bit more misunderstanding here. What is the purpose of the power enrichment orifice? Okay, so the power enrichment orifice is this one here. They call it the enrichment. This would be the power right there. So what activates that, please? Somebody, what causes that to open? Throttle position. Thank you. Very good. When mixture control is set to full rich, which jet limits the fuel flow? What I was looking for is actually the main metering jet. But If you were in enrichment power, the enrichment metering jet, as well as the main metering jet. So these two holes together, the combined area of those would end up limiting my fuel flow. But what I was looking for is the idea that when we are at full rich, this valve will be really big. And my main metering jet, and maybe this one, will be smaller. What does the enrichment jet do? Okay, so when we're in cruise flight, I'll open the right slide here. When we are in cruise flight, we're operating in this zone. This is where we want our engine to spend most of its life. It's what it's designed to do, is to operate right there. And we're going to open our main metering jet, and the designers will have that all set up perfectly to give us, effectively our nice, 14-to-1 fuel air mixture, and we'll get decent power, but mostly good fuel economy. When the pilot really needs power, they're going to push the throttle forward, and they're going to add more air. But the engineers know that the engine will cook itself. It'll detonate. It'll overheat. It'll have all kinds of problems when you try and make it work, really, really hard, full power. So they want the system. They want there to be a system to automatically add more fuel. That's the enrichment jet. So here we're running on the main jet. And in here, we've got our main plus the enrichment. And that is what you're going to see in right there. So here we had cruise, and here we have that extra bonus there when we had that slide there, idle, cruise, and take off. In this diagram here, we've got both of those. It cools at idle and at full power, yes. Well, the main metering, that enrichment metering jet isn't helping us at idle. We do that a little bit differently. We just set the system up to deliver more fuel, but this enrichment is to cool at full power, yes. But you're right, we use fuel as a coolant at idle and at full power. At full power, obviously it's working hard, and at idle we need it because there's no airflow. Typically, when you're idling, you're sitting on the ground. Okay. Okay, unmetered fuel pressure, inlet fuel pressure, yep. Yep. And we're not going to talk about Continental right now because that is tomorrow. What do carbs all have? Twists and turns, separation, yes, absolutely. Why do carburetors, pressure carburetors, and throttle body fuel injections often have poor fuel distribution? Because the intake manifold isn't perfect. But this is a good answer too. In continuous flow fuel injection system, where's the fuel injected? Just outside the intake valve. Love it. Perfect. How does a fuel injection system provide better fuel economy? Better fuel distribution. Love it. Perfect. What type of fuel delivery system is this Bendix that we just talked about evolved from? From a pressure carburetor. Love it. What two factors determine how much fuel the Bendix system delivers to the cylinders? I would say it is the airflow by Venturi and impact tubes and the mixture control. position, and then to a lesser extent also the throttle position. It may have opened the enrichment jet. There we go. Does that make sense? So basically airflow and the mixture control position. Okay, and we don't need to worry about Continental. We'll answer that tomorrow. Is there a float in the Bendix system? There is no float. And what this means is we can fly upside down. If you have a float carburetor, it's got a float in it, which floats on top of the fuel. And it works kind of like the toilet tank in your bathroom. And if you turn it upside down, it works kind of like the toilet tank in your bathroom if you turn that upside down. So there we go. I will save this to continue on tomorrow with the last few questions. I am done with my lecture. Is anyone ready?